behavior. Behavior over here is dependent whether are they classified as brittle or ductile material. Okay. It is dependent on whether it is brittle or ductile. Okay, so let's look at ductile material. Okay, let's look at ductile material. Okay, so for ductile material, the stress ultimate, okay, the ultimate strength, okay, is a lot bigger than the yield strength. Okay, this is for ductile material. Whereas for brittle material, okay, the ultimate strength is approximately equal to the yield strength. Okay, so now when we go back to our stress strain curve, okay, when we go back to our stress strain curve, this over here, okay, this not curve over here is for our ductile material. For a brittle material, the behavior goes like this. Right, brittle material usually has higher Young's modulus. Okay, but because it's brittle, it will just do this. Okay, so over here, this will be the yield strength. Over here, this will be its ultimate strength. This is not very good. I'll change color. This will be its ultimate strength. So it's very similar, okay? Not like ductile material. So therefore, okay, now we apply and then we become critic now. Yeah, we become critic now. So that's where when we apply a ductile material, the factor of safety will be equal to stress yield strength divided by stress allowable. Okay. Where for brittle material, the factor of safety will be equal to stress ultimate strength divided by stress allowable. Okay. Jason, you hit it on the nail. Okay, you realize that once I start drawing the stress strain curve, you realize like shit, right? If we use too low a safety of factor, it means that the material will go into the plastic region. If for the ductile material, we use the ultimate strength. Okay, so there you go. This is the difference between 2P and 3A. Okay. Looking at the material behavior, just a simple formula on factor of safety, when to apply what and why. Okay, right. So this is number one. Okay, so now we are still going to look onto the same thing. And before I go on, anyone, any questions still? Anyone? Anyone need me to clarify anything? Okay, by the way, this is not like 3CO3, okay? 3CO3 is 100% on remembering or understanding, okay? So 3C is just information. 3A is I'm imparting skills, okay? Skill set that you need to use, okay? can we not use U strength for both? Cannot you use to be safe? Yeah, you could. Okay. Okay, you could. But when we learn from the formula, it states that it's equal to ultimate stress divided by allowable stress. Okay, so we have to, yeah, this is a very fundamental formula. Okay, but as I said, I did not know when I was undergrad. Until I'm teaching, then I know. Okay, but I want you all to know earlier. Trevor, you're right. Why not use stress for both? Okay, right. Then the next thing. You all need time to copy or we are good. I know this is different. It's not like the light board, okay, where it's always there. Okay, so I don't hear anything. Now we'll still look onto the table. Okay, and then we at the table, I'm going to look at an example. And you also have this example in your avenue to learn. Okay, it's all there, okay. Yes, so this is the example. This is the structure. Okay. So let's look at this table first. Now, by looking at this table, can anyone tell me? Okay, now I'm trying to make you recall what you learned from 3C. Okay. Any idea how they do the test to get what test do they do to get the data of the use strength and the ultimate strength? Anyone? What type of test? And it's not just mechanical testing tests. What kind of test do they actually do? Anyone, please? Hello? You guys need a beer now. Yes, Eric, you're absolutely right. Uniaxial tensile test. Okay, it depends on what they want to find. So if you look at the top, if you look at the top down here, yeah, tension, compression, and shear. There tension and shear. Okay. So all these tests, remember, I need you all to remember this, okay? Don't be like me when I was a young engineer. I was a fool, okay? I did not know all this, which is wrong, okay? Now, you have to remember this, okay? They are performed, okay, the data or mechanical properties mechanical properties were acquired from uniaxial test configuration. Okay, uniaxial means one direction only. So when one direction, what does it mean? So in tensile, you just pull. Right? We know this. You guys have seen this before. Okay. And then when they want to do compression, they just push them together. They get the compression data. Right? So this is our coupled load. And then over here, in terms of shear, they apply a torsion. Okay. So this is shear. Okay, so T is the torque. P is the applied load. Okay, so from here they do a test, they get all this information. That is why the tests are given in tension, or compression, or shear. Okay, for both ductile and ultimate stress. Now, when we look at this example, so the interloads at a critical section along the steel shaft of a ship are calculated to be a torque of 2,300 pounds. So we have a torque of 2,300 foot-pound or pound-foot-feet, and a bending moment at 1,500 pound-feet, and an axial thrust load of 2,500. If the yield point for the tension and shear are 150 ksi respectively, determine the diameter of the shearing shaft using the maximum shear stress theory. So we will be learning the maximum shear stress theory after term test 1. Okay. Does no data mean they are the same? No. Jeremiah. Good question. No. Okay. When there is no data, does not mean it's the same. Don't do that. Okay. I think like you think like me when we were young. Okay. I'm telling you now. No. Okay. Don't do that. Okay. Now this is real life. Okay. So if I were to sketch out a transformation. Okay. So this is our Y. This will be our X. And this over here is our Z. Can anyone? Yes, I can hear Mike. Any question? No question. Okay. So if you look at this case, okay, is the structure loaded in uniaxial direction? Anyone? Right?
No, it's not
Yeah.
uniaxial.
Yeah. And it's not uniaxial direction, right? So the structure is not loaded in uniaxial direction. Okay, that's for sure. The structure, the example over here is not loaded in uniaxial direction. Then the question for all of us is this. Then how can we, right? How can we apply this data, this table? The loading condition is not the same. Right? It's not the same. It is not unidirection. Okay, it's relative. In relative, you have axial loading, you have torsion, you have bending moment, all applying on the same time. Okay, so when I was a young engineer, I just say, okay, let's ignore the shear. Okay, the shear, let's ignore it. It's not important. You cannot ignore it. You can't ignore it. Okay, okay. So how do we compare apples to apples now? Now on the left hand side is apple, on the right hand side is a piece of cheese. Okay, can we just add them as unit? No, you can't do that. Okay, so how do we do that? Okay, so now let's say that we look at an element. Okay, we look at an element. So let's look at an element on a tensile test. Okay, so let's pick an element. Okay, so this is an element. Okay, so I'm going to do the same in terms of transformation. I'm going to call this my X. This is my Y, and there's my Z. Okay, so we're going to have an element down here. So this is my Y, and this is my X. And then when we draw an element, okay, so this is stress X. Some of you say, oh, shit, I've seen this before. Right? This is unit XO, right? Because the P is applied in the X direction. Okay, so if I label this as point X, I label this as point Y. So this is my stress X is equal to positive. My stress Y is equal to 0, right? So from here, we are going to construct Mohs circle. Okay, Mohs circle. So a lot of you have just been through me pre-CO3, and you may have just seen Mohs circle. So we sketch out Mohs circle with this. Okay, so we have our normal stress, and then we have our shearing stress. Okay. Okay. Element rotate clockwise, element rotate anti-clockwise, and on this line, okay, this line over here, for example, okay, for this example, this is our stress X line, and the 0 is our stress Y line. So from here, we can draw our circle. Okay, we can draw our circle now. Okay, we can draw our circle. Right, that's our circle. So this is our stress 1, and this is our stress 2. Okay, so we if you were to recall, stress 1 and stress 2 are the principal stress. Okay, so what you see over here, okay, all this data over here are the principal stress. Okay, so the tension and compression are the principal stress. Okay, the shear is not a principal stress, by the way. The shear is the maximum shearing stress. So you ask me, Eugene, where is the maximum shearing stress? So this is where the maximum shear stress. Okay, right. What I'm going to do, I'm going to stop here for now, and we come back again on when are we coming back? On Wednesday, but don't go yet. I have something to show you. Okay, don't go yet. I'll stop recording first.